Let's get started on packet structure and protocols. In this section, we will address the following topics. What is a packet? What is a header? What is a field? And what are common fields? We will look at what is encapsulation, which protocols add which fields, and what is protocol analysis. So let's start out with a review of what is a packet. A packet is a message which is sent from one computer to another computer, and it has two main components, the data and the header. The data includes the data which is being sent by the user, in this case ABC, and it's also made up of the header. The header specifies where the packet is going to in the form of the IP address and which program it's going to in the form of the port number. The destination IP address says what computer it's going to, and the port number says what program on that computer is it going to. And as we all know, port number 80 refers to web traffic. What is a field? The header is divided into fields such as destination IP address, source IP address, and port number. So a field is simply a subset of a header. And common fields include destination IP address, source IP address, and port number. But there are other important fields as well, which we will discuss, such as time to live, acknowledgement number, window size, checksum, and protocol. Let's start out with the time to live field. The time to live field is a field which is used to count the number of times that a packet has crossed a router, and it has two purposes. One, to calculate the best path based upon hops, and to prevent endless looping. It can calculate the best path between node A and node B and calculate the best path based upon hops. It can also be used to prevent endless looping. Endless looping is when a packet is forwarded from one router to the next, around and around endlessly, and it just causes extra traffic. Each time the packet crosses a router, it is decremented. So what does decremented mean? Well, it means count down. Here's the example. In this example, the time to live field starts out as 16, and it is reduced by 1 each time it crosses a router. That's what they mean by decremented. When the time to live field becomes 0, then the packet is discarded. Two reasons for time to live: to calculate the best path based upon hops and to prevent endless looping. The acknowledgement number is used so the receiving computer can send acknowledgments to the sending computer so the sending computer knows that the packets are getting through. And one method is for the receiver to send an acknowledgement for every single packet which is sent. Packet is sent, acknowledgement is sent. Packet is sent, acknowledgement is sent. And this is sometimes called ping pong. And the problem is it doubles the amount of traffic which is on the network to have an acknowledgement for every single packet which is sent. A better way to go is to send an acknowledgement only after 10 packets have been received. The acknowledgement number is the sequence number of the last packet which is received, and the advantage is there is significantly less overhead, because instead of one acknowledgement per packet, now we have one acknowledgement per 10 packets. The window size refers to the maximum number of packets which can be outstanding until an acknowledgement is required. And the bigger the window size, the lower the overhead. Sliding window is a feature of TCP whereby TCP dynamically adjusts the window size. If there are a low number of errors on the network, and if it's a good clean connection, then TCP can increase the size of the window, and what that does is result in significantly lower overhead. Another important field is the checksum field, and it's used to determine if a packet got corrupted in transmission. As you know, a packet is nothing but a string of zeros and ones that goes across the wire, and any one of those zeros and ones could get corrupted during transmission. Checksum is a mathematical algorithm used to determine if there has been any corruption. Now here's a super simple example of how checksum could work. When the sender sends a packet, it adds up all of the ones in the packet and puts that number at the end of the packet. And then when the receiver receives the packet, it adds up the number of ones in the packet that it has received, and it compares that number to the number provided by the sender. And if the two numbers don't match, that means there has been a corruption in data transmission, so the receiver sends a negative acknowledgement to the sender, and the sender resends the data. That's the checksum field to determine if a packet got corrupted during transmission. The protocol field shows what protocol is being encapsulated. You usually figure an IP packet is going to carry user data, and that would fall into the category of TCP. But IP packet can also include Internet Control Message Protocol data. In other words, it can include ping commands. The protocol shows what protocol is being encapsulated. A header is divided into fields, and important fields include destination IP address, source IP address, port number, time to live, acknowledgement number, window size, checksum, and protocol. Now let's discuss encapsulation. Encapsulation is the process by which protocols add fields to a message. We know that the TCP protocol adds the port number, and that IP adds IP address, and that Ethernet adds the MAC address. But let's just back up and discuss the concept of encapsulation in regular human communications. And here's an example of encapsulation. A boy is writing a letter to his grandmother. So he writes the letter, and that's the data. He puts the letter in the envelope. So now the letter has been encapsulated into the envelope. The envelope gets put into a mail bag, so the envelope has been encapsulated in the mail bag. The mail bag goes into a mail truck, so the mail bag has been encapsulated into the mail truck. Then the mail truck drives down the road, and when it gets to its destination, the decapsulation process occurs. The bag comes out of the mail truck, the envelope comes out of the mail bag, and then when Grandma takes the letter out of the envelope, she is decapsulating the data from the envelope. Now let's look at encapsulation in the context of computer protocols. Now we have already mentioned that TCP adds port number, that IP adds IP address, and that Ethernet adds MAC address, but there's more to it than just these fields right here. So let's do a closer examination of the protocols and the fields in the protocols. So let's look at these protocols: TCP, UDP, IP, and Ethernet. And this is a simplified diagram of a packet. It includes the data, and then the header includes the IP address and the port number. So this simplified diagram only shows two fields in an IP packet header. Now here is a more accurate diagram of all of the fields that are in an IP packet header. An IP packet header certainly includes source IP address and destination IP address, but there are other fields as well, such as version, or type of service, or time to live, or protocol, or checksum. So let's examine some of the fields in an IP packet header, and you will see that you are probably already familiar with some of them. The first field in an IP packet header is version, and that specifies if it's IP version 4 or IP version 6. The Internet header length field simply specifies the length of the entire header. The TOS, type of service field, is also called quality of service, and it allows us to prioritize certain packets so they're pushed through ahead of the others. The total length field specifies the total length of the datagram. And the identification field is used when the message has been chopped up into many different packets. So the identification number is used by the receiving computer to reassemble the packets into the proper order so the message will make sense. We have a field for flags such as don't fragment and more fragment. Fragment offset specifies where the data begins. And the time to live field specifies how long the datagram is allowed to live on the network in terms of router hops. Each router decrements the value of the time to live field, reduces it by 1, prior to transmitting it. And if the time to live field drops to 0, then the datagram is assumed to have taken too long and is discarded. The protocol field shows which protocol is encapsulated. It could be user data, as in the case of TCP, or it could be Internet Control Message Protocol, as in the case of ping. Of course, an IP header includes the checksum, which performs to determine whether or not there's been corruption during transmission. The IP header, of course, includes the source IP address and the destination IP address. There are additional options, and padding is added if the message is not big enough to fill up the minimum size of a datagram in multiples of 32 bits. And, of course, the last and probably most important field is the data which is being transmitted. So that's an IP header. Now, let's look at the TCP header. And as you know, TCP contains source port and acknowledgement number, but it has other fields as well. So let's look at the fields in the TCP header. The first field in the TCP header is source port and destination port, and as you know, port number refers to what program is being used, port number 80 being web traffic. Acknowledgement number and sequence number work in conjunction. The acknowledgement number shows the last sequence number of the last packet which was received. This performs acknowledgments between the sender and the receiver. Data offset shows the size of the header. Certain number of bits are reserved for future use. And then we have control bits. For example, an urgent bit to indicate that the data is urgent. An acknowledgement bit to determine that acknowledgement is required. Push bits, reset bit, synchronize bit, and finish bit. The window field specifies the maximum number of packets which can be outstanding until an acknowledgement is required. And the bigger the window, the more efficient the transfer is going to be. Checksum is used to check for errors in transmission. We've discussed the urgent pointer. There are additional options here. Padding is used is if the data is not large enough, extra zeros are added to pad out and fill up the header. And of course, the data portion includes the data which is being sent. So that was TCP. Now let's look at UDP, which is similar to TCP, but it doesn't perform acknowledgments. We look at the fields in a UDP header. We see source port and destination port, port number 80B in web traffic, length of the datagram, checksum to look for errors in transmission, and data, the data which is being sent. But notice there is no field for acknowledgement number or sequence number because UDP does not send acknowledgments to the sender. That's why it's has a much lower overhead than TCP. Now let's look at the fields in the link layer or the network interface layer, and two things fall into that category: token ring and Ethernet. We will look at Ethernet. An Ethernet frame format, of course, includes the data which is being sent, but it also adds the destination MAC address and the source MAC address. The preamble is 7 bytes, meaning 56 ones, just a long string of ones, indicating that this is the beginning of the Ethernet frame. So, Encapsulation is the process by which protocols add fields to a message. TCP adds destination port, IP adds IP address, and Ethernet adds the MAC address. Why do we care about packet headers? When we do protocol analysis, we are examining packets, and we do that when we are troubleshooting and trying to determine which packets have been sent, trying to verify the source and destination IP address, and trying to identify the port number. Wireshark is a protocol analyzer that's used to capture and view packets and packet headers to help us troubleshoot problems on the network. CCBC has a copy of Wireshark located on our VDI, our virtual desktop infrastructure, and if you go to that VDI, you will see that Wireshark is the world's most popular network protocol analyzer. So to start capturing packets, I click on Start, and it starts to capture packets. Now you can see some packets have been captured, and here's a packet right here. And if we look at the source IP address, we can see it's 72.21.91.29. Destination IP address 10.0.0.7. The protocol is TCP. It is sending an acknowledgement and even tells us the sequence number, the acknowledgement number, and the window size. Wireshark allows us to look at the contents of packet headers. In summary, in this section, we have discussed what is a packet, what is a header, what is a field, and what are common fields. We have looked at encapsulation, at which protocols add which fields, and we have asked what is protocol analysis. Your assignment is to connect to the CCBC virtual desktop infrastructure, to start Wireshark, to start capturing packets, to ping the default gateway, and then look at the packets that you have captured and try to identify the source address and the destination address and the port number. And this concludes our section on packet structure and protocols.